Hi, I'm Kristen Doty from Catalyst Learning Curricula, and today I'm going to be showing you a workshop on choosing the best error bars to use on a graph. As an AP and IB teacher for high school level sciences, I was always searching for a program that was more accessible for my students, something that allowed them to manipulate their data and the visualization of their data more easily than, say, Excel or spreadsheets. And in looking for that program, I finally found something that I really thought was user-friendly for my students and made it possible for my students to produce a graph that was exactly like they intended. So what we're going to be using is that application today, which is DataClassroom. DataClassroom is a program that was started by another AP and IB science teacher from Chicago. And so you'll find that this particular program is very useful for pulling out the things that you would want your students to discover about their data as they're doing their creating their visuals, but also as a way to understand their data better. So it's a way for the students to do some of the analysis that they should do along the way. The first thing I want to go over in terms of this topic is the concept of why we use error bars. What is the purpose of error bars on a graph, and why do we ask people to include them when they're analyzing their data? And the simplest answer for that is that we have transparency as science teachers to reveal all of the strengths and the weaknesses of our data. And error bars allow scientists to do that by exposing the variation of a group of samples, such as you might see with your error bars on the spread of data or the distribution of data points that were collected. The error bars can also be used to reveal the probability of error for the mean or any other descriptive statistic that is used to describe an example or a sample group or an experimental conclusion. So when we're revealing that information to our reader readily in our graphs, it allows the reader to understand better what's happening and what's the probability of error or uncertainty for everything that is shown on a graph. And that type of transparency allows them to make their own decisions about what conclusions they would make from the data that are presented. But also, if we use certain error bars, we can also use those error bars as predictors for the possibility of the outcome of a hypothesis test, such as the significance between, if there's a significant difference between two sample groups. So what exactly do error bars represent? This is a complex question because, and probably the most important one to consider, because the error bars that are given on a graph are never standard. They're not always going to represent the same thing. Every person who's creating the graph has the choice of what to put on their bars. They could be using the minimum and the maximum so that the error bars are depicting the range of data. The error bars might be created using the standard deviation above and below the mean, or they could be demonstrating the quartiles around the median. It is also possible that the error bars have 2 times the standard deviation, or maybe they're the standard error of the mean, 1 or 2 times the standard error of the mean in the representation. And then it's also very common to see error bars that are representing the 95% confidence interval. So any of these different choices might be made, plus many, many others. And the error bars on a graph cannot be assumed to be expressing the same thing. There are certain tendencies, but nonetheless, because everybody can make the decision they want, typically error bars can be used in a way that misleads or can create bias just as well as revealing information. So that variation that's being expressed, or the uncertainty, should be defined, and a student should ensure that their error bars are well described in a figure caption or on the graph itself. However they choose to use, whatever error bars they choose to use, they should be ready to defend that choice. So the student should be able to say why they didn't do error bars for one style and why they did do them in the style they chose. So how can they make that defense if they don't know exactly why they choose what they choose? So to get into that, the most common conventions or the acceptable trends that we see in scientific presentation of data are the use of error bars as standard deviation above and below the mean when the graph is representing a variety of samples. So in this particular graph, you have one dot showing the mean, and the error bars above and below are the mean plus or minus one standard deviation. So that's what's shown here in the caption. The representation that's made by this particular type of graph is multiple samples at each of these different x-axis measurements. So you would never have a standard deviation for a single data point. You can't calculate a standard deviation for a single data point. So you know that if there's standard deviation is being used, it is several different observations or measurements that are centrally tending around this particular mean. And when there's a smaller standard deviation, you had a smaller spread of data. So this is a distribution representation. Standard deviation commonly is used for multiple measurements and an expression of the distribution of measurements, including what is likely to be a normal range for the next measurement seen. Whereas the standard error of the mean, or two standard errors of the mean, or the 95% confidence interval, all three of these are used instead to describe the entire research study. So the entire experimental group or the entire experiment, so that it can be compared out to other experiments. The standard error of the mean or the 95% confidence interval, which I'm going to use fairly interchangeably in this session, are discussing or representing the bigger picture of what happened with this entire experimental group or this entire experiment, whereas standard deviation is looking at the next observation or a group of observations. Those are just conventions. It's entirely possible that the error bars might be chosen with another descriptor, such as min-max or quartiles or any other description of their data, real or actual data points or abstract data points that are pooled together to describe the set. If the standard practices or conventions are not helpful and do not adequately reveal what happened in what was seen in the observations, then a person making the graph might decide to go with a different, less conventional description. For that reason, it's really important to know what's the difference between these different types of error bars and why we would choose one over another. To explore one of these concepts, I want to take you to DataClassroom and do some comparisons of how standard deviation and standard error of the mean and the 95% confidence interval are related. I'm going to talk about the relationship in terms of equations as well as some other comparisons. But in this first comparison, I want to look at sample size. So this is a data set I brought in that has sample sizes from 3 samples all the way up to 500 samples. Each group of samples were randomly chosen using a computer-generated random number chooser. And so you can see with 3 samples, we have a spread, these being the 3 data points, with 5 samples, 5 data points that seem to coalesce into a smaller distribution. And then 10, we see about the same spread that we saw with 3, just slightly larger, and so on. When we get up to 500 samples, we have a range that's broader, of course, than what we saw in some of the smaller sample groups, but still centrally located around the mean. And what's shown here are error bars here on the side is the mean plus or minus 1 standard deviation. So I've chosen the descriptive statistics on this graph to be standard deviation. And you can see that the standard deviation is quite resilient to changes in the sample size. So when you have a different size sample from very small to quite large, we still see the standard deviation is fairly consistent. I can actually bring those notes up on the graph of what the standard deviation is for these different samples. Of course, my graph gets a lot smaller, but I want to show you the breakdown of that. With 3 samples, you can see the mean here and the standard deviation, the standard error of the mean, and the confidence interval. So you have a nice description of the descriptive statistics here on this chart that gives you an idea of how stable the standard deviation appears to be with these random samples. So if I switch that to a different measure, from the standard deviation, I'm going to switch it to the standard error of the mean. And with the same data set, you can see that the standard error of the mean is dramatically smaller than the standard deviation, of course, but it also gets dramatically smaller with increased sample size. So the standard error of the mean is greatly impacted by this sample size, which makes sense because the calculation for standard error of the mean is the standard deviation divided by the square root of the mean. I'm sorry, it's the standard deviation divided by the square root of the sample size. So if the sample size is playing a role in that equation at being in the denominator as it is, then it makes sense that it would be dramatically influenced by the sample size changing to a larger and larger number. Likewise, if we change those error bars to be 2 standard errors of the mean, we see just a doubling of the size of those error bars, and 2 standard error of the mean are quite close to the 95% confidence interval, but not perfectly. So if we toggle between 2 standard error of the mean, which is what's visible right now, and the 95% confidence interval, you can see that change in the 95% confidence interval is quite a lot larger than 2 standard errors of the mean when the sample is very small. So with these very small samples, we see a greater difference between 2 standard errors of the mean and the 95% confidence interval. But otherwise, people tend to use these 2 calculations pretty interchangeably when they discuss their data and the level of potential error. So I'm going to toggle between those one more time. So this is 95% confidence interval, and this is 2 standard errors of the mean, both of which are quite dramatically impacted by the sample size, and yet they tend to look identical when the sample size gets to be larger. You stop seeing much of a change between 2 standard errors of the mean and the 95% confidence interval somewhere around here on our visual. Now remember, these are randomly generated data, and so as I toggle between them, you can see that the difference between them is quite dramatic in the smaller sample set, but pretty much the same when you move from 10 samples up. So we tend to interchange these 2, the 95% confidence interval and 2 standard errors of the mean, but it's also important to understand the relationship with n. So in thinking about that, which error bars you use might be partially based on sample size and how much your data are impacted by sample size. Student data tends to be very small. They tend to use smaller sample sizes than this 500 sample size example. So if you think about your student data being somewhere maybe within 10 to 40 samples, this is the range where we're looking at the how the impact of the sample size changes the students' outcome of their expression of error, and then also looking between these 2 of which choice they'll make, in that there's quite a bit of impact in these smaller sample sizes to use these 2 interchangeably. That is the standard error of the mean and the 95% confidence interval. So let's look at one more thing that might influence the choice of what type of error bars a student chooses to use. The error bars, particularly in AP and IB classes, students are taught that their error bars, if they create the error bars correctly, can be used as a predictor of a statistical hypothesis test. Now, I would not suggest that you use this in lieu of a statistical hypothesis test. It should simply be a confirmation that the statistical hypothesis test was calculated correctly to see this agreeability between the graph and the outcome of the statistical hypothesis test. But generally, if the error bars are made using the 95% confidence interval or two standard errors around the mean, then it is possible to get an estimate of what the outcome of the statistical hypothesis test might be. And a statistical hypothesis test is like a chi-square test or a t-test, these types of hypothesis tests. So if the error bars are made with the 95% confidence interval or two standard errors of the mean, and there's no overlap between them, then it's likely that your difference between the two experimental groups is significantly different. If they do overlap, then it's not likely there's a significant difference in these two experimental groups. The reason being that this error bar is representing how much above or below the mean is this particular sample group is likely to fall if the experiment was repeated 100 times. So in 100 repeats of the same experiment, we expect the mean to toggle a little bit above and below within a certain range. What that range is being defined by the 95% confidence interval. So if this error bar is made using the 95% confidence interval, then we would expect the mean to bounce around anywhere in this range with the expectation of 95% of the time it will fall somewhere in this range. Likewise here, this has a much larger range because there was a lot more variation in this particular experimental set. But even if this next experiment was done over again and the mean fell at the top end of the range for this group and the bottom end of the range on this group, they still do not overlap. And so they would still be significantly different from one another, so that this group was different than this group. That cannot be said with the second graph down here. If the mean on repeated experiments were to toggle from the top to the bottom of this error bar, and let's say the next time we did it, we got to the bottom of it, and the next time that this experimental group was retested, it toggled towards the top, then the overlap would still put them within range of each other. And so we don't see a significant difference between these two groups because they could go anywhere, they could fall anywhere in this whole range in a repeated experiment. So one thing that's critical to note is that you cannot use this trick with the overlapping error bars as an indicator of significant difference between two groups if you have made error bars in any other manner. So if you use minimum, maximum, or standard deviation, or two standard deviations, or one standard error of the mean, none of those different error bars would allow you to do this prediction of the outcome of a statistical hypothesis test. So beware if you've told your students otherwise. They can only use this little quick trick if they're using the 95% confidence interval or two standard errors of the mean for their error bars. So just to back that up, remember that the relationship between standard deviation, standard error of the mean, and the 95% confidence interval is something that can be taught to students both in a visual form as well as in a numeric form. And so just as I was showing the standard error of the mean and the difference between standard deviation and standard error of the mean and the 95% confidence interval on this graph, it's really helpful to show students that relationship over and over so they understand the standard deviation will be a larger error bar compared to the standard error of the mean because of the calculation that is used to find that information. So you can see the standard deviation is a larger error bar, the standard error is much smaller, and the 95% confidence interval is typically about twice the size of the standard error. So what is that relationship that it's depending on that shows this difference? These are all the same data set. The green bars are all the same. Why do we see this difference in how the error bars are made? That is simply because of the calculations. So these are the calculations that are completely interdependent. You start with the variance equation, and as you see, the standard deviation is the variance equation here at its inside the square root. So the standard deviation is simply the square root of variance. That's the initial relationship. And variance, as you can see, is a comparison of every single observed data point against the mean. Those square differences are summed together in the numerator and divided by the sample size minus 1. So the sum of the square differences divided by n minus 1 is the basis of standard deviation. So we're looking at something that is going to be impacted by the mean, each observation, and the size of the sample. In order to calculate variance, you end up squaring all of your units. And so standard deviation is simply the square root of variance in order to correct for units. That calculation goes on to be the basis of the standard error of the mean. Notice that the numerator is the standard deviation here. So the standard deviation is simply transferred to this equation and divided by the square root of n. So when I said that the standard deviation is less impacted by the sample size, and the standard error of the mean and the confidence interval have a greater impact based on sample size, as we saw in these relationships. That's because the equation introduces the sample size again in the standard error of the mean in the denominator. So the square root of n is going to reduce the standard deviation. And that's why you see that reduction being dramatic between standard deviation and standard error of the mean. The 95% confidence interval is the calculation that is done here is identical here. So that is the standard error of the mean multiplied by 1.96. So 2 SEM, this is the standard error of the mean SEM. 2 SEM is simply 2 times this, whereas the 95% confidence interval is 1.96 times this. So they're used interchangeably because these calculations are very similar. Does that mean they're the same thing? This is a question that came up during the live workshop because this is something that a lot of people are shortcutting in science. They say, well, you can use 2 standard errors of the mean or the 95% confidence interval because the calculation is so close. So error bars made with 2 standard errors of the mean and the 95% confidence interval are given here. And you can see the equation is the mean plus or minus 1.96 times the standard error of the mean, or the mean plus or minus 2 standard errors of the mean. Almost the same calculation, which is why we see these numbers being used interchangeably. What is the 95% confidence interval? So the standard error of the mean and the 95% confidence interval are almost like 2 sides of the same coin. The 95% confidence interval is the probability upon repeated experiments that the mean will fall within a certain range. So if you were to collect data on multiple times, repeating the same the same sample number, but doing it through a population, you're going to have the mean move around in a little above, a little below what is seen before, until you get a distribution that's in a normal distribution curve. Assuming that you get a normal distribution, the mean of the entire population in is thought to be here, but the mean for a smaller sampling, such as is done in an experiment, which is lowercase n, would be falling somewhere within this normal distribution. If this is repeated 100 times, it is thought that 95% of the data should fall within 2 standard errors of the mean, which would give it a range from here to here. And note that 5% of the time it will fall out on these tails, which we declare in science to be the area of acceptable probability of error. So we are including our region of expected probability of the next expected mean to fall within this 95% zone, since 95% of the time the mean will fall in this area. So that's what the 95% confidence interval is including. It's saying, okay, well, we have a mean and we're expressing it to be at the top of this green bar, and 95% of the time we would expect it to be a little bit higher or a little bit lower, and therefore that range is what is under this bell-shaped curve within 2 standard errors of the mean. The precision of that is a little bit off by 0.04, and therefore you see a little bit of a difference in the calculation itself. So let's mess around with a data set and see what we can find in terms of practical use of error bars and decisions being made. This is a data chart for an experiment on breath holding. And this is just a simple experiment that my students could generate their own data by collecting information right there in the moment. And the first thing I would say when teaching error bars or when teaching data analysis is ask the students to collect their own data in that moment. And that way they have a relationship with the data and they're able to understand and relate to what was happening and what those trends might indicate. So in this experiment, student A, a student in my class, was asked to hold their breath and time themselves, self-report the data on this spreadsheet. They did 5 trials and they can, within the beginning of class, and therefore how many ever seconds they had, they just put it on the chart. Then I asked them to take 1 minute of deep relaxation with their eyes closed, breathing deeply. So after they did 1 minute of deep relaxation, they then held their breath 5 more times and recorded their data across their row for 5 trials. So what we have are students who have all collected 5 trials as their baseline, and then 5 trials after the treatment being 1 minute of deep relaxation and deep breathing. What we get is a mean for each row and the standard deviation of each row. And that standard deviation really only applies to this student's data for this set of trials. So these 5 trials have this mean with that standard deviation based on this variance. And you can see that that same student with these 5 trials has a slightly different mean with a different standard deviation. And so each student can relate to their own row of data and because it's personal, whereas another student is going to have a different mean, a different standard deviation. However, as a class, we would have the class data as well. So I have my students take a look at this data set and then think about which remarks they might make based on what it is that they're going to talk about. If they're talking about individual data, then they should be talking about the mean for the individuals and the standard deviation for that individual. If they're talking about the class data, then they would be talking about the mean for the whole class. But in that case, they would look for the standard error of the mean because they're looking at the entire experimental group. Again, standard deviation when we're looking at a set of measurements for a single sample, and standard error of the mean when we're looking at the probability of error or uncertainty of this particular mean for the entire group. So when we take this data set, I actually put it into tidy data format first. And what that means is I took the trial for student A with the before they did the treatment, and the trial for student B before they did the treatment, and so on, and put that into just columns of data. So they have prior to relaxation, and then they have after relaxation. And each of these students, A, B, C, D, has their trials listed in seconds in a third column. So we have 3 columns: the treatment, the student or the subject, and then the number of seconds of breath holding. And what I do is I just need to copy this URL and go into DataClassroom, and I can, from DataClassroom, I can go back to my dashboard, and from my dashboard, I can upload a new data set. So I can either create a data set using a blank template, or I can import this data set from a worksheet. Since I've already got a worksheet, I'm going to go ahead and fetch that. It's going to confirm that that I'm the right person for this. So I put in my URL, that's the source of my spreadsheet, and I ask it to go fetch, and it's going to make sure that I'm the person who has permission. So it's going to check my login information, and it'll only do this the first time that I log in for the day, but it will, I just wanted to show you that screen so that you knew what it's doing. And then I have 3 tabs on my data set. I have the 3 tabs on the base. I have the breath holding raw data, and then I highlighted some of the data points, and then I changed it to tidy data format. And so when I'm bringing that in, it's going to ask me which of those 3 tabs do you want, and I'm going to import the tidy data format because it's already ready with some of the information I wanted to consolidate. And I didn't need to bring in the variance and some of those other things. So I just confirm that and it brings it in, and you can see that it has my title here from my data set. It has the treatment above each of my columns, and I'm going to talk about my treatment in terms of type. It is categorical data rather than numeric, and so I'm going to choose categorical. My subjects are my students' abbreviated names, A, B, C, and so that is also categorical. And then the duration of breath holding in seconds is going to be numeric data, so I'm going to label that as such. And then I'm going to go into the graph. Now at this point, I could get some help with my graph by using the graph wizard. I'm going to show you that in a moment. But I can let it lead me through some graphs, but I'd like to show you some, well, might as well show it right now. The graphing wizard allows us to take some questions about what types of information we have, and it leads us through this in a question format so that we're making good choices. So you can have different types of data. Is it proportions, change over time, the variability or the shape of the data, comparing groups, or is it the relationship between two numeric variables? And that's what we're aiming for here. We want to know if there's a relationship between the information that happened before or after. And so you can see it's just going to take me to the next step and the next step. I'm going to close out of that wizard right now because I want to show you the type of graph that it would eventually lead to. But you can follow the wizard and it will allow you to make choices all the way along the way. And then it shows you how to change your graph to incorporate the choices based on the questions that you answered. So in this case, I'm going to have my students pull up their data and choose what they want to do with manipulating it. And doing that, I'm going to first take a look at the difference that I pointed out here with the colors. If my students were to graph the individual data for each student, then I would want them to graph the standard deviation. And so as they explored that, they would say, okay, the subject is the x-axis, and the treatment that they're doing, let's do this with a scatter plot, the treatment that they're doing, or I'm sorry, the duration of their breath holding would be plotted for each student. And you can see that student A has 10 data points, but they are not color coded right now. All that we can see is all 10 data points fall out together. We don't know which ones happened prior to relaxation and after relaxation. And so to fix that, I'm going to add Z in there as my color coding, and it's going to add prior to relaxation and after relaxation. If I don't like those colors, I can go to my treatment group and pool those colors to be something different. Maybe I want to show them in green and red here. And so I can choose to show them in any one way that I want to. I can also go in there and exclude one. So you can see right now that they're overlapping. And if I just want to take a look at what happened before, where their data fell out before, I can do that in this way. Or I could have both shown at the same time, or I could switch over to the other so that it's only after relaxation. It's hard to compare them though when they're on two separate graphs. So I could either take a picture of this graph and show it as this, just copy it. It's going to go to my clipboard and I can stick it into a slide or into a document. But I still want to show the difference between them. So I'm going to actually go back and include both in the same graph. And I'm not wild about that color. I'm going to change that color to something a little gentler. And then I want to go to, I want to see my descriptive statistics because I want to see, is there a difference between these groups ultimately? And so I want to first look at my standard deviation for each student. So I press descriptive statistics, and it's going to automatically give me standard deviation because that's the last thing I did. So if it had shown me instead the 95% confidence interval, that's not a choice I would give my students. I do not want them showing the confidence interval because this is just student data for each sample between multiple trials. The more appropriate statistic to use would be the standard deviation. And so I would ask my students to choose standard deviation. But as you see, the standard deviation lines are right beside those little circles. And so I'm going to first make these little circles a little bit smaller, and I'm going to make those lines a little bit more robust so that you can see them more clearly, and maybe make my mean dot a little bit bigger too, so that it's easier to see that spread. Now, as you can see now that it's a little bit larger, that the size of these standard deviation bars are spanning the entire data set. They aren't broken up by the treatment. And I really do want to see those standard deviations be separate, because as you remember, the standard deviation for one group, 6.7 of this mean, but it was 4.7 for this person's mean. So we know they're different standard deviations, but I need to tell it to separate those out. And so if you remember, the treatment group is in Z for me, and therefore I'm going to group my descriptive statistics by Z. And what you see happen is that each one of these students now has the standard deviation of their 5 trials for after relaxation separated from prior to relaxation. So I can actually look at the difference between what happened with student A before and after the relaxation and deep breathing. And it's easy now for me to visualize whether the breath holding capacity went up or went down. So with student A, they had a longer breath holding capacity after relaxing, but student B had the opposite. Student C, it went to a longer duration. D, E, F all went up in duration, but G seemed to stay about the same, with about the same standard deviation. So the error for these points could be really predicted to be anywhere for student G, and not likely to go in one direction or the other. However, the general trend is that prior to relaxation, the students' trials were shorter, and after relaxation, they tend to be longer, with a little bit more standard deviation in the second group, it appears. But that's not the case for all of them. And for that reason, I want to make sure that my students have looked at their raw data very critically and graphed the raw data so that they can see that not every single time did this go up. If we look at student L and G, they seem to stay about the same. But if we look at, oh, that's not true, I'm sorry. If we look at L, it actually went down for the most part, and so did student B. And so we can have these differences, and the student can talk about these students who were not following the main trend, where they did in fact actually have a shorter duration after relaxation, and maybe even talk about those separately in their conclusions. It's not often that a student would put their raw data into their conclusions or even into their lab report, but it really is important for them first to graph their raw data so they can see if there are stories underneath that are individual stories that must be discussed as outliers or possibly as disruptions in the main trend. Most of the students will jump immediately to the mean for the entire sample group, and I want to show you that as well so that you can see how that would be different than the analysis that occurs here. So in this analysis, I could also take away these the dots and just leave the error bars. In that case, I might change the colors so that the colors are a little easier to see. That yellow is very hard to see. But again, just going up here and changing my color will do the job so that I can have something that's easier to visualize on my data set. So you can see that. Okay, so what I want to show you now is if I go from the individual data where I have used the standard deviation as the error bars, and instead I'm going to switch to the class data, I want to use the standard error of the mean as my error bars because I'm looking at the entire experiment in that case instead of the individual trials. So if I changed over to the mean, I'm going to change my x-axis. Instead of being students, I'm going to make it the treatment. And after the treatment, we have prior to and after relaxation. I want to break it up so that it's by duration. So that's my y-axis, and these error bars are now quite robust. I can give them a little bit of a break here. They're kind of bigger than I need them to be. So I can bring them down to be more visual. Or I could do what the students typically do, and I can make a bar out of this. So classic student reaction is to make a bar graph and leave the dots out. And so they often will do this. And that's descriptive, but not nearly as descriptive as seeing the dots so that they understand the spread of the data. So the error bars in this case are giving a hint of the spread, and the dots can reinforce the spread of the data. These error bars are made from standard deviation. So we want to switch that to standard error of the mean or two standard errors of the mean. If you're an AP or IB student, often students will need to show two standard errors of the mean or the 95% confidence interval. Although typically in medical journals and published journals, scientists do use standard error of the mean, one standard error of the mean. The high school students tend to instead use two standard errors or the 95% confidence interval. So when I put those up, you can see that it's very close, probably still overlapping. If I show this as the graph without the dots, which is classic for the students, it's less descriptive, but it still does have the basic concepts of the mean and the standard error bars made from the 95% confidence interval. I do want to point out, even though bar graphs with the error bars on them is the default for most of my students, it's their preferred visual, I do want to point out that it is a strange choice because error bars the bar graph goes down to 0. And if you recall, none of my data went down to 0. And so it does visually represent something that actually wasn't present in my data set, which is those bottom area shown on the graph as if it were a significant part. So I want to show you two things you can do to make this even more visually pleasing. And one is you can put your error bars in the middle and have a little bit more transparency in the line so that they can overlap if you want to show both at the same time. You can also change them out of that bar mode. I'm not a big fan of the bar mode, and instead just do a line or a line with a dot or just the dot. So know that you can choose any of those different possibilities by just toggling between these and moving the dots to be the right size. So if I was going to put them overlap, I think I would put them off to the side. So left or right in this case. So there are lots of different choices, and I want my students to make those choices and make good choices as they do that. The last thing I would have my students do is make sure that they put a title on here so that they're talking about the duration of breath holding with, so so that they can put all of the things together that are required. Notice that there's also a comment here on the error bars that says that the error bars are above and below show the 95% confidence interval. That way it's described right there underneath the graph as a figure caption as needed. So all of the manipulation I want my students to do are present in DataClassroom, and therefore they're able to quickly move through the raw data analysis. All of the things we did with data analysis were allowing us to take a look at how the standard deviation of the raw data breakdown for each student's trials was easy to visualize, and we can look for changes in the trend for individuals before we talk about the main mean and how the mean for each of those treatment groups before and after differed. So it's a good companion for the students to go through this, even if they're not going to print those graphs or show them in their data, show them in their conclusions or their presentation. They should do the analysis of the raw data so that they know what the mean is representing, and they can tell if there were some disruptions in the mean. So having the students understand there are plenty of different choices to be made, and those choices should be defensible. Again, the students should fall out towards looking at standard deviation for individual multiple trials, individual sample groups with multiple trials, and they should be looking at the 2 standard errors of the mean or the 95% confidence interval when they are looking at the mean of the experimental group. So all of that is helpful for my students to be able to manipulate things quite easily and to maneuver around it. I'm going to see a greater level of data analysis in that case. The next thing I want to show you is that the raw data, if they're not normally distributed, can be quite a problem. I'm going to show you a data set that is not normally distributed. And when the students look at this raw data set, they tend to go, I have too many windows up. When they go look at this raw data set, they tend to see them as the same thing. So often when students will jump towards this bar graph of the mean with the 95% confidence interval and feel like they're accomplishing the right graph for the right data set. So this is an example of a control group and 2 treatment groups where a mutagen was used that was suspected to alter the expression of a single gene in mice. And the mice had a tail length, a measurable tail length difference in the phenotype if the mutagen was impacting that particular growth gene. And so each of these different groups have different chemical exposure. You had the control group with no chemical exposure, the treatment group A and B with exposure at different times of their life cycle of gestation or being reared. And you end up with a tail length measurement for each of these groups. If you look at a comparison between the control group and the treatment group, or treatment groups A and B, you see no difference in the mean. They all have exactly the same mean. And this is a manipulated data set to give that visual, but it's helpful to look at what's going on. If the students create a graph that looks like this, their conclusions would be that the chemical exposure does not seem to impact the tail length, the expression of the gene for tail length. That conclusion would be incorrect. Not because the error bars overlap. The overlapping error bars concurs that there's no significant difference between these sample groups. And the conclusion appears to be that there's no difference between the mice that were not exposed to the chemical mutagen compared to those that were exposed, regardless of the treatment group style A or B. However, if we unhide, so this is the 95% confidence interval. If we do 2 standard errors, the mean, likewise, we would come to the same predictive conclusion about the hypothesis test. However, the problem with this data set is that the error bars are correctly placed. The mean is in the, is expressed as is, but the data are distributed in a way that does not give them a normal distribution. So if I unhide the dots, these are the individual data points. And you can see that the individual data points for the control group are clustered very tightly around the mean. And therefore, the mean is expected to be repeated multiple times. It would still fall here. But in treatment group A, you have bimodal data. You have data where the tail length was around 2 and the tail length was around 5. But you don't have any mice or any observations of mice with a tail length that's actually in the area of the mean or in the 95% confidence interval of the mean. And so this is not a good description of the data. Remember, our 95% confidence interval is supposed to be a predictor of multiple experimental sample groups and where the mean would fall. So as a predictor, we would expect all the means to fall within this normal distribution. But instead, what we see in our data set is that the tail length is nowhere near the mean. It is falling to a longer tail length or a shorter tail length. The problem with that, or the reason for that, is that when the data are not distributed normally, the mean is not a good description of your data. The mean works very well with normally distributed data because you have that bell-shaped curve and the mean is in the middle. But with bimodal data where you have 2 different sample groups, the mean falls between those 2 different groups, and it is not a real data point. It doesn't have any reflection of an actual observation. Instead, it is an average of all of the observations, and it falls in a place that is not actually describing any of the data. So when you have the 95% confidence interval or the standard error of the mean, either 1 or 2, you end up with a description that's based on the mean. And yet there is no, the mean is not a good description to begin with. And so basing the standard error or the 95% confidence interval on something that's already a terrible description of this particular data set causes problems. Instead of these blue bar graphs that you might see where we would say there's no significant difference between the control group and the treatment groups A or B, we should instead be saying these data are not normally distributed, and therefore we will not describe them with the mean or the 95% confidence interval or the standard error of the mean. When we get to sample group B, we see that the treatment group falls into 3 different clusters. And again, this could be trimodal data, or maybe it's just skewed data. Maybe we have, most of them here and some of them here, outliers. But what you're seeing in terms of the observations is you saw many mice that have no tails whatsoever. And so those mice without tails obviously have had some impact on the gene expression of tail length, whereas the other mice either had a tail length of normal size that we see in the control group, or much longer tail gene expression. So a gene that was turned on or knocked out. So with this particular group, it would be also incorrect to come to the assumption that the chemical exposure had no effect on the gene for tail expression. And that conclusion, the error that the student would be making if they did not have the distribution data of the actual raw data, is that they're pulling together their data into statistical description before they have decided whether or not their data are falling in a normal distribution. So how do we alleviate this problem? Asking the students to describe their data first as raw data. So showing all of their raw data and distribution patterns of their raw data first to justify whether or not they have a normal distribution can be the very first step in their data analysis. After they have affirmed that they have a normal distribution of their data, they can go on to use descriptors that are reflective of a normal distribution, like the mean or the confidence intervals with their error bars. But if they mess up that first step, then they're off to their usual habits without any sort of confirmation that those usual habits are a good choice. So with my students, the biggest hindrance I see is that they don't want to graph their raw data because it's tedious. And if I can take them into DataClassroom and have them graph their raw data in many different ways, just as I demonstrated with their the breath holding data, where they can look at those data points in different ways before they get started, or with the mouse tail data, that first step becomes less difficult, and it leads so naturally to the next steps if they're going to progress on to showing the mean of their sample groups. I also have the ability for my students to take a look at the actual numbers when they're looking at these. The automatic calculations show up here, and they can trace each of these numbers to make sure they understand what's going on with their data in the notes on what the calculation for the mean, the standard deviation, the standard error, the 95% confidence interval all are before they move on. And they may or may not show those notes in the on the graph or in their data set that they put into their report or their presentation, but they can, and they're welcome to take a picture of it just using the automatic photo version with the data set calculations present on the graph. So know that they can do both and move those clipboard snapshots to whichever presentation they're going to use. So when we take a look at data that are not normally distributed, we end up with these problems that we discussed with the mouse tail example data set. And basically the bottom line is, with the normal distribution it's a fantastic choice to use your classic descriptors of normal distribution, mean, median, mode, these kinds of things, with standard deviation, standard error, and the 95% confidence interval. But if it doesn't pass the first test of the raw data being normally distributed, then none of those choices are an adequate choice. Instead, they should graph their raw data and include that discussion of the fact that they have bimodal or skewed data in their presentation, rather than moving on to this misleading conclusion graph that would cause the reader to go in the wrong direction during the conclusions. So to bring it together for you, the couple of things that are take-home messages is, when you're making error bars and you're making choice of error bars, first graph your data, your raw data, to determine if you have a normal distribution. Next, if you have a normal distribution and you want to discuss the multiple samples of multiple measurements of a particular sample group, then discuss it in terms of the standard deviation with your error bars. If you want to discuss the outcome of the entire sample group, to compare groups against each other or to compare groups with other experiments, then you make the choice to go to standard error of the mean or the 95% confidence interval. If you're going to be comparing error bars as a means to jump to a conclusion about the hypothesis test and the statistical significance of your two groups, then you need to use two standard errors of the mean or the 95% confidence interval in order to make that comparison of overlapping error bars. The last thing to think about is, be careful when looking at error bars. Don't make an assumption that anybody is using the convention that are the accepted conventions, because those change between different groups of science and math, and those conventions are not always followed. So they need to make sure that they always report what it is that they're doing, either in a key or in a figure caption or directly on the graph, and to only state comparisons of significance when they're using two standard errors of the mean or the 95% confidence interval for their group, the data for their sample groups. And then finally, if you need more than one graph to tell the story or the underlying stories, then it's a great idea to include more than one graph to make sure that everything is revealed and transparent. I hope that was all information that was helpful and applicable to your subject area. If you have any questions, please feel free to contact me at Catalyst Learning Curricula. My information is here, or Aaron Reedy at DataClassroom. His information is here. It was great having you.